In this video, we are going to discuss the calculation methods for a uniaxial stress state for a certain hardening behavior of a material. As you can see, the curve in red is a behavior that we're actually looking for. But as in the nonlinear case, you already know that there are some parameters that you know from material tests, for example. However, the rest of the curve is something that you can trace by knowing certain properties of the material at certain time periods. So, and of course, these inputs are given by means of actual mechanical tests that are carried out on the material properties. Now, let's say that we have to trace this particular path for a material. And along this path, you have a certain linear region, which can be clearly seen as a straight line. And I continued that by means of the yellow curve, which is also following the same tangent. And that is for the linear behavior of the material. But at some point, of course, there is some kind of plasticity, which is a contribution both of elastic strains and plastic strains, and follows the path which is moving more towards the right with the point B on it. Now, let us assume that we already know what the value of the stress is at the point A, and that is given as sigma A. And sigma A lies to be on the elastic region in this property. At the same time, we would like to find out that if I have an increment in strain such that I go from strain epsilon A to strain epsilon B such that the change is given as delta epsilon, what would be my corresponding stress? Therefore, I can write here that sigma A is known and sigma B is something I need to find out for a strain delta epsilon, which can be given as epsilon B minus epsilon A. And what is also known to me is E is the elastic modulus. Now let's say that with some material tests carried out, we already found out that there is a certain stress given as sigma Y, which corresponds to a point C, which defines yielding. These are some things that we already know. Now, let's apply a certain strain delta epsilon to this structure when it is at point A and try to find out what happens beyond this point. So we need to trace this curve, as I said before. And the only thing we know about it at this point is that it has a certain elastic modulus given as E. So if I apply a certain hypothetical strain delta epsilon, then I will end up within this elastic region, hypothetical elastic region at a certain point, which will correspond to this strain epsilon B. And this will land at a certain point here on this tangent. Let us assume or call this point B1. At this point B1, we can find out a certain stress, which also corresponds to a certain point on this curve, which we need to trace, and it's called point D. Now let's also say that by a characteristic or material tests that we did, we also know that in this region there is a tangent stiffness given, a modulus given as ET. Now the stress at this point therefore can be written as sigma D because it corresponds to the sigma at the point D along this curve. Now in general, we can say that the tangent stiffness ET at the point C is same as the elastic modulus E. So when this strain delta epsilon is applied, we end up with a certain delta sigma trial value, which can be written as sigma D minus sigma A. Therefore, this region, because we have this over here, we can say this is sigma delta sigma trial. Yeah, and this is purely based on the elastic property, so we can write this to be E times delta epsilon. However, only a fraction of this is purely in the elastic region, and it lies before the point of yielding. So if I have to draw this out on the curve, I would say that out of this delta epsilon, only this area is actually lying in the elastic region, while the rest is lying in the plastic region, which is this part. So we can find out a fraction of this delta sigma trial by using a value called beta, which is actually a fraction that lies between 0 and 1. So we can say a fraction of this delta sigma trial at the point C is such that yielding occurs. So we know that sigma naught from the yield function is equal to sigma y. So using this relation for yield function for at Fc, we can write this to be equal to sigma A, which is of course already something known to us, plus this change in stress, which is only the fractional change that we want to consider because this is the part which is in the elastic region. Of course, this is the mod, minus sigma y is equal to 0 because this is the point of yielding. And from our previous exploits, we already know that delta sigma trial is equal to sigma d minus sigma a, which we can substitute back over here in the equation. So as a simple reminder, this part consists of the change in strain, which is elastic, and that depends only on the elastic modulus E and the change in and the delta epsilon. So a certain fraction of it, which is now part only of the, which corresponds to now the elastic strain, can be used to define the yield function such that we are only up to the point C. So we get the yield function at point C to be equal to the total stress up to that point, which includes sigma A, which is known to us, plus a certain fractional value of the total delta sigma trial that we found out, minus the yield stress that we also know from tests. So we are able now to calculate the value of beta, which comes out to be sigma y minus sigma A by sigma d minus sigma A. Now moving on, we also have to find out this change that happens between the point C and B. So we still have this strain in this region which has to be applied as delta epsilon CB. So delta epsilon CB can be written as epsilon B minus epsilon C. And epsilon C is in the elastic region, so we can write epsilon B minus sigma C by the elastic modulus E. So now we can get a first estimate of the stress increment from the point C to point B by using the standard relations for tangent stiffness at the point C now instead. So if we use a first increment, we have delta sigma 1, which is the first step, I would say first increment, which will then be given as the tangent stiffness at the point C times the delta epsilon CB, so which can be written as epsilon B minus epsilon C, and that can be written as E epsilon B minus E epsilon C. E epsilon B of course corresponds to this point over here, which is given as sigma D, and E epsilon C corresponds to this point over here, which is given as sigma C, which is also known to us, which is sigma Y. Now this therefore is the point B1. So we can also write over here that sigma B1 is equal to sigma D. Right, so we have sigma B1, which is sigma D, and we have sigma C, which is also same as sigma Y. Now what we can do is we have sigma D at the point B1, so we can now calculate again using the tangent stiffness at the point B1, which is given as the tangent stiffness at the point D. So at the point C, we can now plot the tangent stiffness which corresponds to the point. So at the point C, we can draw the tangent stiffness which corresponds to ET at D, which is the same as this one. So these two parts are now parallel. So I can draw this particular tangent, and when a strain delta epsilon CB is applied in this region, at the strain epsilon B, I will get a new point over here, which can be written as B2. So we can calculate this whole step, which was done for delta sigma 1 using the ETC, also now for ETD. So I'm going to move on to the next page. So I can write over here that for the next step in stress, that is delta sigma 2, we can write ETD times epsilon B minus epsilon C, because the step is still the same. We still want to find out between the 2 points, but the first part was the elastic, and now we find out the plastic region. And we can say therefore sigma B2 is equal to sigma C minus delta sigma 2. So we have the 2 points now, B1 and B2. Now in order to find out a certain value or estimate of the value at the point B, what we can do is we can find out the average of the values between B1 and B2 to come as close as possible to the point B. So it's possible that by doing an average between points B1 and B2, I end up somewhere close to this point B, which can be written as B3. And that is one of the methods that is applied generally to find out the next level of the stress. So this is just one of the numerical methods, as I said. There are many others, many other invariants of the same method as well. But this is just an example to show you how the increments can help in the same way as it did for geometric nonlinearity. So if we average these two stresses, then we can get a certain stress at sigma B3, which can be written as sigma C plus, because that's the yield stress, plus the next part, which is the average of these two stresses that we have found out. If I open it up, I can get this to be equal to half of the tangent stiffness at C plus the tangent stiffness at D, which come from tests, times the change in strain, which is just an input because of the change in load or displacement applied on the object. So the reason why I wanted to give you this example over here is that we will continue in the further videos to discuss the incremental calculations based on for formulation of small strain and then computational procedures, and we will keep using some of the terms that we used here or the way we calculated some of the things, so it would be easy for you to make a relation to what actually happens in the incremental process. Of course, the post-yielding part has been shown to you here is part of the Euler two-step Euler integration. So you can also find this in standard numerical analysis books. But this is just a flavor of how you can use incremental stress calculations to find out your curve for your material nonlinearity.